The last speaker today is Professor Jeffrey Case from Pennsylvania State University. His title is Conformally Invariant Boundary Value Problems and the Nonlocal Operators. So let's welcome him.
Okay, so I would like to begin by thanking the organizers for the kind invitation to come here. It's always nice to come back to Taiwan. So I also want to thank Alice and Paul for, I might not have known them as long as many of you, but I've certainly gotten to know them very well in the past 8 years or so. They've been very good mentors and also very kind bringing me here. I think this is my 5th time in Taiwan, so I especially want to thank them for all the support and nice opportunities they've given me. So today I want to talk about something somewhat related to what Yiwang was talking about yesterday, but I want to take a different point of view. And let me explain it by starting with one way of thinking about what Escobar did. So Escobar was studying the boundary Yamabe problem. And to study the boundary Yamabe problem, you want to start out with some nice variational formulations. And the observation is that if you take this functional, integrate the scalar curvature on the inside, and then integrate the mean curvature with some constant that I don't remember on the boundary, then this is variational, which just means that if you differentiate this and you have a conformal path or a path of conformal metrics, then this ends up being integral of whatever your path is times r, and like that. So I'm not going to be very precise with the constants or anything. I'm just saying there's a variational formulation for prescribing mean curvature on the boundary and scalar curvature on the inside, and then you can try and do variational methods to solve the boundary Yamabe problem. I can recast this in terms of operators, in fact, conformally invariant operators in the following way. If you define the conformal Laplacian the way that you normally do it, so let me just write it this way. J is the trace of the Schouten tensor, so I don't have to put in extra constants. And I define this operator, which I will denote B01. This is the conformally invariant Robin operator. So here my mean curvature is normalized so that it's actually the average eigenvalue of the second fundamental form. These two operators, they have the property that, I'm always talking about n+1 dimensional manifold, and if I start writing m's, I mean the boundary. So same notation we've been seeing throughout. Yeah. So the main point is that these operators, they're conformally covariant, and you can see that their constant terms are exactly what appears right here. So you can just rewrite this as some sort of energy involving these two operators. More importantly, if I were to write down the conformal covariance law, which I won't do, but if I were to write it like in Marugame's talk before, these both act on densities of the same weight. So you end up with the conformally invariant functional. So let me just write it here. So this implies that if I write down this functional here in a slightly funny way, I take the energy of the conformal Laplacian and correct it by this boundary term, and I forgot to change it, like this, then this is first conformally invariant. So I can change my metric however I feel like within the conformal class. The second nice property that this has is that it's symmetric. In other words, I'm just saying I'm dealing with a PD over here which is actually self-adjoint. And from these two observations, you can basically do all the analysis you're familiar with. So let me just say one more thing before trying to move on. The point is that if you assume, for instance, that the first eigenvalue of the corresponding boundary value problem here is positive, then it turns out that if you compute the energy of a function, so this is some nice symmetric form, compute the corresponding energy here. This is always bounded below by, following notation that E used in her talk, it's always bounded below by the corresponding energy of a canonical extension. And the canonical extension here is the one that solves L2 UF equals 0, and U is equal to F on the boundary. And this here is for all U which have prescribed trace. Okay, so I'm just rewriting the Dirichlet principle in terms of these conformally invariant operators, and everything works out the way that you would expect it to, at least under a spectral assumption. So I want to reinterpret this in a different way. Yes, so that's one of the things that will come up, but I'll just jump to it. This is exactly the same as saying that the Yamabe constant, the boundary Yamabe constant, either one is positive. It's just like in the closed case how you argue that. And if you are talking about a Poincare-Einstein manifold, this, by work of Jack Lee, actually follows from the assumption that the boundary has positive Yamabe constant. Yeah, let me not say more about that quite yet. So the thing that I want to try and do in this talk is explain how this connects to non-local operators, something that I've gotten into with Alice recently. So what you can do is you can define this map. F gets sent to B01 UF. So if you're in the case of the upper half space, in upper half space, there's no curvature. You're just talking about the Laplacian and the normal derivative. So over here, you're taking a function, you're harmonically extending it to upper half space, and then you take the normal derivative. So this is the usual Dirichlet de Neumann operator, which is the same by work of Caffarelli and Sylvester as the half Laplacian. So I'm going to think of this as a conformally invariant half Laplacian. Okay, it has the same symbol, and it has the conformal invariance property because these act on densities of the same weight. So what I've written over there, in a very strange way, you might say, is that if I look at the energy of any extension of U on the inside, sorry, any extension of F on the inside, this is bounded below by the energy of this non-local operator on the boundary. And another way of thinking about this, which I like to take even though this will definitely get me in trouble, is on this side, what you're really talking about is on the interior, that's just essentially the energy of the Laplacian, so it's like the W12 norm of U. On the inside, over here, I can think about this as the 1/2 norm of F on the boundary, so this is like writing down some sort of Sobolev trace embedding of W12 into H1/2. Okay? So that's kind of nice. We're bounding U in terms of information on the boundary. So let me give a little bit more information about this operator so that this really looks like Sobolev trace. This surprising fact, in a sense, and this is really a result of Guillemot and Guillaume from 2007 to be somewhat vague. What they essentially say is that this operator B1 that I defined is exactly the same as, let me call this P1. This is the fractional GJMS operator. So again, let's cut out a lot of explanation so I can get to the non-local or the nonlinear version. But if you have a Poincare-Einstein manifold, you can talk about scattering for the Laplacian on the inside, and then you can talk about the operators that are sort of the Dirichlet de Neumann operators at infinity. Graham and Zworsky studied these things, and they showed that under a spectral assumption, which follows automatically from this, you can always define the operator. What Guillemot and Guillaume said is that if you take the perspective over here, write down this Dirichlet de Neumann operator, and then compute the fractional GJMS operator for the solution of the Loeffner-Nierenberg problem. So this is if P1 is defined with respect to G plus being the Loeffner-Nierenberg metric, then these two operators exactly agree. So I'm actually writing down an operator that has been well studied from a different perspective. No, all you need is constant scalar curvature. You combine the asymptotics of Anderson, Crucial in them, and then your work still applies because the trace term is the right thing. So last thing to say about this is this operator has been well studied on the sphere, or B1 has been well studied on the sphere, or you can just use a conformal transformation to put this all in upper half space. And so the overall conclusion, let's say it this way, the overall conclusion you can derive by thinking of things this way, but there's another way to do it by Escobar, is that I don't remember the year. The other thing you can do is you can rewrite this as a trace inequality the way that we're more used to. This energy here is in fact bounded below by LP norm of F, and because I've specified dimensions, I can tell you what these are, and there's an explicit constant here. To be more precise, what I'm really saying is the following. As long as you take some metric, where the metric is a metric on, say, the disk, and then the ball has its standard metric or something conformal to it, you can exactly prove this inequality with a sharp constant. And from there, you can start studying the boundary Yamabe problem the usual way by blowups. Okay. So what I want to try and do is sketch how these ideas extend to other operators, other types of curvature problems you might consider. So the first one, and how I started thinking about this, was Alice and I wanted to understand better what happens for the higher order fractional GJMS operators, or another way to think about it is we wanted to think about what might happen if instead of boundary Yamabe, you talk about boundary Yamabe for Q curvature. And the general picture looks something like the following. So let's call this the fourth order case. So let me write a big theorem and say where the contributions come in. So of course I wasn't the first one to think about this. The original ideas originate in this work of Alice and Jie Qing from 1997. In the case of dimension 3, n is the dimension of the boundary again. And in the more general case of higher dimensions, there's work of Branson and Gover from 2001. And there's some more. Well, there's some work of Andreas Yule. There's some work of students of Gover, master's students, and then some stuff that I did. Put it all together, the theorem that will look a lot like how I started is the following. There exists operators, which I will denote by BJ3. So these, you're thinking of them as boundary operators for the Penates operator. They have the property that, well, let me write this strangely so I don't have to write density spaces. The first one is that if I think of the Penates operator, and I think of these operators BJ3, and what these operators are basically normal derivatives to a particular order. These are conformally invariant. Okay, so without writing any formulas, I'm just saying that you can find operators which the leading order term counted in terms of how many normal derivatives you take is sorry, here I should say J is between 1 and 3. If you take For any one of these values of j, you can find some operator which is conformally covariant, acts on the same space of densities as the Panitz operator does, and the leading order term is normal derivative that many times. So of course when j is 0, this is nothing, it's the trace, it's the restriction on the boundary. When j is 1, this is basically the same operator I wrote before, but you have to change some constants because you're changing the bundle. In higher order, it's complicated expressions, but you can write them down explicitly, it's not too bad. It's just evaluate u on the boundary. Yep. The second part is that these operators are nicely compatible with the Panitz operator in the sense that you again get some sort of symmetric form. So I'll call this q sub 4. I'll write this the way that you should expect me to. So I'm going to take the energy on the inside of the Panitz operator, and then on the boundary I'm going to correct terms in the following way. Sorry, this should be B13U, B23U. If you want, this is really B03, but again, that's the trace. So the correction in this case is you just pair these boundary operators, so the total number of normal derivatives adds up to 3. And the statement is that it's automatically conformally invariant because of part 1. But more importantly, it's symmetric. And again, symmetry here just means that we have some formally self-adjoint boundary value problem when we use these operators as the boundary operators. Okay. So a few comments about the history of this. In dimension 3, what Alice and Jay were mostly interested in doing was studying the functional determinant, and they wanted to know how do you consider the functional determinant on manifolds with boundary, what's the right boundary condition to use, and they're really only looking for B3. They do talk about this as well, but the main focus is make some assumption on the mean curvature on the boundary, figure out what the corresponding boundary operator should be. Then Branson and Gover just looked at that and did everything in higher dimensions, and they wrote down candidate operators. They found invariant operators, but they couldn't prove the symmetry unless you had some special structure like Poincare-Einstein around. And then formulas, explicit formulas were added later. This argument here is just by tractors, which was part of the problem with symmetry. Later, explicit formulas come which allow you to check symmetry. Okay, so what this means is we can study boundary value problems involving the Q curvature on the inside and these boundary curvatures on the boundary in a conformally invariant way by studying this energy. All I'm going to talk about now is how it works for traces. So one of the things you can say fairly immediately is the following. So again, this is also in the work of Branson and Gover where they can do things because of Poincare-Einstein, but the theorem is the following. Suppose that the Panitz operator is positive, which I'll write in the following way. So what I'm really saying is suppose that the first eigenvalue of the Panitz operator, when you assume that the restriction of u to the boundary and its normal derivative are both 0, so the natural Dirichlet problem, assume that eigenvalue is positive, then you can extend. Meaning I have the same type of inequality as before, and this is sharp in the sense that equality holds if and only if you solve some sort of extension problem. So I should put in another thing here. The restriction of u to the boundary is f, and the normal derivative essentially of u is psi. And this is for all u with the trace prescribed. Okay, so this statement, this is just the first eigenvalue where you prescribe that the Dirichlet boundary condition is 0 for both things. This is the trace and this is the normal derivative. Yeah. You can formulate similar statements for other boundary value problems. There's also like the Navier type problem with this as a 2 similar statements hold. I'm just writing one of them down. So the upshot of this is that, again, you can think of extending. And in fact, in the work with Alice, what we did is we thought about this type of extension in the case of Poincare-Einstein manifolds. And the comparison works in the following way. So I can, in this general setting where I'm not assuming anything about the interior except for that spectral assumption, I can define operators F goes to, well, let me be more careful. So I can define an operator which just maps F to the pair, F and psi to the pair as you expect. Sorry, this is a U. So under the spectral assumption, I can just do the canonical extension. I can consider taking derivatives. I'm going to think of this as a pair of operators B3 and B1. And what I find is that for a general function, as long as I've prescribed the traces, the energy is bounded below by some energy on the boundary. And I'm going to be sloppy at this moment and explain why. Okay. It's B2. So what I'm... let me get to that in a second. So I'm making the choice of the boundary operators just because of how I've set up the functional originally. The subscripting problem here is because what I'm trying to do is I'm trying to tell you what the orders of the operators are. So I'm taking my function u and I'm extending it up to the inside by a 4th order operator. This operator here is using the 3rd order derivative of f, so it ends up being like a 3rd order operator. This one is taking the 2nd derivative of the 1st derivative, so it's like a 1st order derivative. Yeah. So the point really is that if I think of this as an inequality giving me some sort of Sobolev trace embedding, I'm saying that W22, which is what I get on the inside over here, is bounded by, this is more or less the H3 norm of F because of the derivatives, and this is like the H1 norm of psi on the boundary. So I'm again rewriting one form of the Sobolev trace embedding. Okay, now I wrote this in a funny way where you don't see the dependence of the cross terms. And the reason I did that is because of the work with Alice, which is going to be the big motivation. With Alice, we showed that on Poincare-Einstein manifold, so if this is originally Poincare-Einstein, so this has been defined many times, but I'm really thinking that over here I'm working with some compactification. It doesn't matter what the compactification is, but if I know that the inside is Poincare-Einstein, it turns out that this operator that I called script B3 is exactly, I think the constant is 2, it's exactly up to some multiplicative constant, the 3rd order fractional GGMS operator. So this is some conformally invariant operator whose leading term is the Laplace to the power 3/2. This script B3 is B33 acting on the extension. Yeah. Let me finish the statement and come back to that. This is the surprising thing. So the statement is that this is actually correct in the sense that if you change psi, but you keep f fixed and consider the extension and then define this B3 the same way, actually this is the same. So what I'm really saying is that for Poincare-Einstein metrics, you can recover this fractional GGMS operator P3 without canonically extending first. You just need to find some extension, which is in the kernel of the Panitz operator where the trace itself is fixed. You don't care what the first order derivative is, in a sense. There's some sort of magic cancellation that happens. It's only true for Poincare-Einstein. The reason that this works is that if you write down the Panitz operator for a Poincare-Einstein manifold, it factors as a product of second order operators, so you can just use that product structure to solve things. Without it, no hope. But the corollary of this that I also want to mention, and this is work of Antonio Ace and Alice, and I have a different version of this, but we'll say it's them. What they prove is, well, yeah. B1 psi. Yeah, thanks. Yeah. Yes, you can also recover P1 this way, and it doesn't care about what F was. The corollary, the cheap way of getting at the corollary is you just combine these assumptions. So if you're on, say, hyperbolic space, or your favorite compactification of hyperbolic space, and Alice and Antonio wrote it in a few different natural choices. So on hyperbolic space, you have a sharp Sobolev trace inequality, which is simplest to write this way. The constants are known. And there you go. One constant, another constant. Okay, so the idea is nothing more than as soon as you have this identification, these operators P1 and P3 on the sphere, they're completely understood, and there are already Sobolev inequalities, sharp Sobolev inequalities proven by, say, Beckner in that setting, and you just put everything together. Okay, so again, once you're at this point, then you can start studying the boundary Q curvature problem if you want to, but there's been very little work done on that at the moment. So the way that Alice and Antonio did it is they wrote this part down very explicitly for a specific choice of compactification, the one that we call the adapted metric. So it's the one where you choose the Q curvature on the inside to be 0 already and the mean curvature to be 0 on the boundary, and then you can just write things in spherical harmonics. But if you have already the invariant operators, like I've said up here, then it's a one-line proof. Okay, so rather than try and use this to do any hard PD, because I don't feel like doing hard PD today, I want to try and do this now for fully nonlinear problems, something like what E was doing. So to do that, let me remind you of a few. Actually, before I do that, let me make the minor comment that all of the work of Branson and Gover works for general K. So they have boundary operators like what I was writing down here for the higher order GGMS operators, and they have the symmetry property as long as you know your Poincare-Einstein. So you can do something like this, wherever. You can write down the functional and know it has the symmetry properties already. And then work of Gover and Sillen says that you have a similar decomposition here in the Poincare-Einstein setting. So it's really just some magic that happens because of the product structure. Okay. But let's move on to a fully nonlinear case. So in the fully nonlinear case, there's two questions. The first one is how do you set up the functionals, and then the second is can we get all the way to Sobolev trace. The functionals part is actually relatively easy. So if you define sigma k the usual way, so I will usually just write sigma k, but it's really something that is determined by the metric on the inside. This is defined as the kth elementary symmetric polynomial of the Schouten tensor viewed as an endomorphism. This thing, it's known due to one direction is already in the first paper by Vyakovsky. And then the other direction is due to Branson and Gover. I think this was 2008. It's known that sigma k on a closed manifold is variational if and only if k is small or G is locally conformally flat. So you'll remember at the very beginning when I set up the Escobar problem, I needed the variational structure to start studying the boundary Yamabe problem. The variational structure is going to be important for us here to set up our energies like that. Okay, the next fact is that, so this is closed case, that's how you should think about it. The next fact, this was proven by Sophie Chen in 2009. What Sophie showed is that there exists some boundary invariance HK, which, again, the formulas are known, but they're not terribly important. They have a form something like this, though. So they're like sigma k. Actually, I don't think it's like sigma k. Let me write it and say it better in a second. So what do? You form all sort of sigma k combinations of two different tensors. One of them is take the Schouten tensor on the inside and restrict it to the boundary. The other is take the second fundamental form of the boundary. You form them together to make sure that they have the correct homogeneity. So this is homogeneous of degree 2k. This has to be homogeneous of degree 2k minus 1. That's how you choose these. And then you take a linear combination of all possibilities. And then Sophie shows that the pair sigma k hk is variational in these cases. So if k is 1 or 2, or G is locally conformally flat. So you can hope to study the sigma k problem variationally in these cases by using this. Let me make one comment about this. That is, J is parameterizing how many copies of J there, or how many copies of, yeah, something like that, yeah. Yeah, so the only thing about this formula besides that it's homogeneous that you really need to know is that L, this is the second fundamental form. The second fundamental form, it depends on only the normal derivative of the conformal factor when you change conformally. So you see a first order normal derivative here. If you look at the Schouten tensor when you restrict to the boundary, naively you expect that it depends on the full 2jet of the conformal factor, but in fact this only depends on, let me write this like E did, this only depends on the tangential second order derivatives of the conformal factor and, so we'll put a W there, and the normal derivative. So in fact, these two things are independent of second order normal derivatives. Okay. So the first observation that E and I made is that if you start from these invariants, sigma k and hk, you can cook up a functional straightaway that allows you to study this variationally. So the theorem, which has a form very similar to what E wrote yesterday, is the following. Yeah, I'm just writing the highest order terms. If you haven't noticed, I'm really lazy when I write what things depend on. Okay. E wrong, yes. We will make this less ambiguous. Okay. All right, so the theorem is the following. There exists two operators. Well, under these assumptions, k equals 1 or 2 are locally conformally flat, there exists two operators. One of them I'll denote Lk. What this is it's a multilinear operator. It takes in 2k minus 1 arguments, spits out a smooth function on the boundary. And then there's a boundary operator Bk with the same domain, but it produces a function on the boundary. And it has a number of properties. The first property is that these are conformally covariant, which is a pain to write, but I'll do it anyway. Conformally covariant in the sense that if you change the metric conformally in the following way, so I will use the, let me keep my laziness. So here capital N is the dimension of the inside. So I change conformally this way. This should look like how you normally do scalar curvature 4 over n minus 2, except now the numerator is also scaling. Change the metric this way, then this operator, let's use W's, scales as, there's a power out here which we can all compute by homogeneity, so I won't write it. And then on the inside, you just multiply by u everywhere. And similarly for B. So I'm just saying we have these now multilinear conformally covariant operators, and they act on densities of the same weight. That's the first property. So what I'm saying, let's walk through this in two cases. So in the case where k is 1, we're talking about the scalar curvature. When we're talking about the scalar curvature, L1 is confusingly what I called L2 before. It's the conformal Laplacian, and that just acts on functions. If you're talking about sigma 2, and you want to try and write sigma 2 in terms of a conformally covariant operator, you have to write it in terms of a 3 linear operator. It has 3 arguments. That's what the 2k minus 1 is saying, and so on. The second property, which links these to the invariance, is that the constant term is known. The constant term, the way that we normalize everything so that later statements make sense in the critical case is the following way. So if you plug in 1 to the conformal Laplacian, you know that you get scalar curvature, except you have a constant n minus 1 because there's this funny Branson trick that gets you Q curvature. Same thing is happening here. These operators in the critical dimension, they annihilate the constants, and this constant is chosen just so that things I write actually extend to the critical dimension using Branson's trick, if you want. And likewise, BK has this type of property. So these operators recover our invariance. The third property is that the energy U1 up to U2k, just integrate what you expect. Okay, so as you can see, writing this gets kind of annoying, but all right. The energy is symmetric, so again, we have a self-adjoint boundary value problem if we want to think about prescribing, say, sigma k and hk in some way. Okay, so, oh, I didn't write what I said. This is symmetric. Okay, so if you remember E's talk, you don't have to, but if you remember E's talk, she used this symmetry to very easily compute the first and second variations. And we're going to do the same thing. I'm also going to use the conformal covariance to, well, the way we do it in the paper is the conformal covariance gives us convexity pretty easily. So the theorem, the main theorem here, which I'm actually not going to prove because I don't have the time, is the following. So why we set everything this way, again, we'll make it clear who Wang is. So the theorem is the following. If you let CF just be the cone, let me in fact make this 0 so that things are easier. This is just the set of all U such that this metric GU, which I wrote up here, so that this is in the positive cone. In fact, you can work in the closure, and you also want to say that the restriction to the boundary is 1, so that we're talking about some nice Dirichlet problem. If you work in this cone, then Q is convex. Well, let me write it this way. The map U goes to Q. This is convex. in the cone. So in particular, this allows you to say that if you look at the energy of Q and you try and compare it to things, there is in fact a unique minimizer, U naught. I want to say that if I start with a fixed metric on the boundary, there's a canonical way to extend it inside, so sigma k is 0. Yeah, so this is the analog of what I was saying before. You can put an F here, but that's fine. So what I'm saying is you can minimize this functional in the class C naught, and the minimizer is unique. So equality if and only if U equals U naught, and U naught solves our equation. Okay. So it's the same exact statement as before in the linear cases. In the fully nonlinear case, the proof of this goes through work of Beauguin. Beauguin proved, well, he didn't really write it this way. He proved the existence and uniqueness of solutions to these type of Dirichlet problems where instead of 0, you have something positive, so you're actually in the interior of the cone and have elliptic estimates. But his estimates actually allow you to run down to 0 as long as you're talking about C11 functions. Okay, so the minimizer here actually is not necessarily smooth, it's just going to be C11 in general. Yeah. It only has the boundary condition on the trace. It's just like for the conformal Laplacian, you only need to prescribe the restriction of U to the boundary. You don't need higher order things. That's what this part is. Beauguin is just solving he's just solving the Dirichlet problem. He doesn't need this normal operator because he's not doing it variationally. He's doing it by a comparison method. Yeah. Yeah, so the reason that I'm introducing the B is because I want to think of it as a fully nonlinear operator, and I want a final Sobolev trace inequality. And in the interest of time, let me just write the last theorem and what it would imply. So if you wanted to have a Sobolev trace inequality for this type of operator, the L's that I'm saying here, what you would need, well, there's a number of different ways that you could prove it. One way you could do it is you could prove uniqueness of the critical points that solve your problem, which is really the same as the following. So suppose you have a metric, G, it's in the cone, well, on the boundary. This is on the upper hemisphere. It satisfies sigma k, G equals 0, and this hk is constant. So the point is, if I, in the theorem over here, minimize the Euler equation, the inside is going to have sigma k be 0. Then if I try and minimize where I prescribe the boundaries, so I'm talking about LP type Sobolev trace inequalities, the Euler equation will be hk equals constant. So the Euler equation for the Sobolev inequality I've not written is this. I want to characterize the solutions to this. I can if I put in one additional assumption, which is weird, and it's suppose also that the mean curvature of this metric inside is not varying too much. So it's a pinching condition. The conclusion is we know what G is. G is flat. So this is an Obata type theorem. We know that on the hemisphere, there is a nice Einstein metric, in fact, which satisfies these two conditions. It's just the flat metric on the ball. And our theorem says that as long as you put in this pinching condition, you can get uniqueness. And the proof is Obata. It's exactly like how Escobar proved his original theorem by Obata. And the hope, and I'll end here, is that this will prove that if you look at this energy, it's in fact always bounded below by U to the appropriate power, which for the sake of time, let me just write this way with an explicit constant, but we still are kind of far away from this. In particular, we don't understand why this should be here or how to get rid of it. Say that again? The mean curve, sorry, this is M, not X. Mean curvature on the boundary, yeah. Okay, so let me stop there. Thanks for your attention.
Any question or comment?
I definitely hope this condition isn't necessary, but
I see. Okay.
condition that you're in the cone might actually already. We haven't been able to prove that though. The other hope is that there's just another estimate that you can get. The thing that's strange about proving Obata theorems, in closed manifolds, Obata theorem is just use the divergence identity in this fancy formula and you're done. For manifolds with boundary, you can only prove an Obata theorem if you know that the inside is Einstein and there's a conformal vector field which is normal to the boundary. And you need to use that condition. So maybe there's another condition like that that you need to rule this out.
Does your proof, it doesn't mean that it's sigma kg equal to 0, hgk equal to constant, it's solvable.
No. No, we haven't thought at all about if you can actually minimize this functional by, say, some sort of concentration compactness type lemma. Yeah.
So if there is no more question, let's thank the speaker again.